Hello everyone. I would like to continue with the previous video. We kind of stopped where I'm going to set this y double prime equal to 0 so I can find the point of inflection for this particular function. So let's just review a little bit before we continue on. This function is given to me as x to the exponent 3 plus 3x squared minus 9x plus 5. And when I graph this, I got a shape of the graph like this. And for me to find the extreme points, because I don't know whether or not it's a max or a min, what I did was I take the first derivative and I set the derivative equal to 0 because right at this point, if you draw a line tangent to this curve, it has to be a horizontal line. Okay, so I will draw like obviously it's a horizontal line. At this horizontal line, the slope has to be equal to 0. So I set the slope equal to 0. After I set this equal to 0, I can solve for this equation. Solving for this equation, I have a quadratic equation. And to simplify the process, I divide each of these terms into 3 so that I can simplify my equation to this. And then I factor. Using factoring, I figure out x equal to minus 3 or x equal to plus 1. And if you see right here, x equal to minus 3 and x equal to plus 1. So then I substitute this value into my function. The function that given to me is right at this point, I want to figure out the value for y. Right at this point for x, I want to figure out the value for y. Okay, so the process was to substitute x equal to negative 3 into the original equation. Do the calculation. I have this equal to 32. So the points I have here is negative 3 and 32. And then when I have x equal to 1, I substitute into the equation. I figure out it's equal to 0. So then it's a good idea to double check. So I went up, I double check. The point is there and there. All right. Okay. So it's pretty close. It's pretty good there on the graph. And then we label our coordinate negative 3 and 32, 1 and 0. And when we label this, before we know it's a max and before we know it's a min. So we obviously know that on the graph, but we have to use the derivative test in order to prove that it's a max or a min. So using the second derivative test, I have to, from this first derivative, I have to find the second derivative. And then at this point, this function is such an easy one for us to differentiate. So I have 6x plus 6. And then at that certain point here, at this point here, I substitute the value of x into this equation. I see that the second derivative y double prime is less than 0. Then to remind myself, I draw the SAS phase, realizing that this SAS phase, this point here will be a maximum. So I put a maximum. And then at this point, as a minimum, I have substitute x equal to 1 in here. I obviously is the positive values, so it's equal to 12. So then I remind myself, if it's a positive second derivative, then he's smiling, then that means the point right here is a minimum point. Okay, so before I got into the point of inflection, because I kind of rushed in previous video, then I want to zoom this, and then I want everyone to take a look at this graph here compared with this graph. Okay, so what you have is this, right? So we have y double prime equal to 6x plus 6. So I sketch this graph on here. So here is my y double prime, because I should put right here is y double prime. Okay, so I have 6x plus 6 is a linear equation. And then I would like you to project this maximum point. If we project this maximum point down to this part, do you see this is a negative, right? So obviously it is a negative. So whenever you are in doubt and you want to ask me why you tell me that the y double prime negative, I am going to have a maximum point, then the graph here will prove that. So this part of the graph is actually negative. Okay, so I'm going to tell everyone that this is a negative. Yeah, so right here is a max. So here is my negative part of the graph. Alright, so if you go to the minimum points and then you project it down to your graph, okay, you obviously see that it is a positive, right? So it's a positive. And obviously I have this smiley face. Okay, so now to find the point of inflection, okay, I will set y double prime equal to 0 and then solve for x. So I'm going to continue with this. Okay, so let me give myself some space. Then solve for x. Okay, so I solve for x. So what is my double prime equal to? My double prime is equal to 6x plus 6. So 6x plus 6 equal to 0. So I should have 6x equal to negative 6. So I will have x equal to negative 6 divided by 6. So x is equal to 1. Negative. Okay, so x equal to negative 1. So when x equal to negative 1, what is the value for y? Okay, so y at negative 1 will be equal to, don't forget, always substitute this into your original equation right here. Okay, so then I should have negative 1 raised to the exponent 3 plus 3 times negative 1 square minus 9 times minus 1 plus 5. Okay, so working with this, I should have negative 1, negative 3, or positive 3, because don't forget you take negative, you raise to the exponent 2, so you have a positive 1 here, you multiply by 3, which is positive 3. I got plus 9 and plus 5 in this case, so I should have this equal to 16. Okay, so 9 plus 14, 17, subtract 1, I should have equal to 16. So therefore the point of inflection is when x equal to negative 1, y is equal to 16. Okay, so let's go to our graph to see where this point is, because the whole point about point of inflection is point of inflection is when you see that the curve is kind of changing from the state of concave down to concave up or vice versa. Okay, so I just want to fix this part if you don't mind. So to find point of inflection, okay, set y prime equal to 0, then solve for x. So let's go to the graph and find that point. So we are having negative 1 and 16. So right here is negative 1. I project it, I go up here. I got it right here maybe. Okay, so right here is 20 and 15. So I divide this into this part. That should be somewhere right there. So this is my PI. PI. So I will put it negative 1 and 16. Alright, okay. So it's obvious, right? You see your curve is going concave down and then suddenly change to concave up, where this part of curve is your point of inflection. Alright, so let's see if I have anything else to say to everyone. All right, okay. So I have a few questions I would like everyone to work with. And I do give you the result here, but you need to make sure that you figure out and then show me that you use the proof, like the second derivative test, to tell me the maximum or the minimum point. And the best is to make sure that you work on this and then you check the solution that I posted to see the expectation of what you must do in order to prove a maximum and minimum point to obtain the full marks for on the test. Okay, so this is the part of this exercise is review for Unit 2 test, and I will indicate to everyone that you must prove your max and your mins by using the second derivative test. All right, okay, so do I need to say anything else? So the whole lesson have two example, and I introduce the concept of the maximum and minimum point, and maximum and minimum point occurs where the slope is equal to the slope of this tangent line is equal to 0. And I summarize all of this into this smiley face and this sad face right here. And then we work with one example where we just find maximum and minimum point, and we use second derivatives to prove it. And then for this example, we have a point of inflection, so we figure out the point of inflection as well. Okay, so a point inflection is to set the second derivative equal to 0, solve for x, get the value for x, substitute it into the original equation to solve the other value for y, and it's a good idea to double check on our graph to see if it's a match with the graph that we sketch. Alright, I don't think I have anything else to say. I hope you like the lesson, and I hope you like the concept of having this smiley face and this sad face right here, so then we don't have to memorize any of the rule or formulas. So hopefully we find some fun in doing mathematics, because I know that everyone think calculus is daunting, it's very hard, but I think it's a lot of fun. And in your electrical electronic programs, you find there's a lot of useful applications. And in the next few lessons after this, we will learn all the application involving electrical electronics. All right, thank you.